Okay, so the previous day we learnt about the phase velocity, that is given by omega by k, and the group velocity given by d omega by dk. As the name suggests, group velocity, the concept of group velocity only comes when you have a group of waves that are superimposing with each other. In the previous lecture, I took three waves of different k values and different omega values, that is different wave numbers and frequencies, that were superimposing with each other, and we got this mathematical expression. And I told you that by superimposing waves of different frequencies, we will get a wave packet. This was the envelope term. So remember, this wave inside this oscillation inside this packet moves at a velocity of the phase velocity, moves at the phase velocity Vp, and this packet itself moves at the group velocity. So phase velocity is the velocity of the waves underlying the envelope, and group velocity is the velocity of the envelope itself. So a particle, the concept of a particle is something which is localized in space. So this velocity of a particle is always represented by the group velocity but not the phase velocity. So the group velocity, that is the velocity of the wave packet, represents the velocity of the particle, or the velocity of the transference of energy. So what we had, I had considered three waves, and then I told you if you increase the number of waves, then what you have for group velocity is d omega by dk. Now there is an interesting feature which we can relate it to the uncertainty principle, which we had discussed in class. Now remember what the uncertainty principle told you. It told you that the uncertainty in the measurement of position and the uncertainty in the measurement of momentum was always greater than or equal to h cut by 2, if you remember. So the statement said that you cannot precisely measure the position and the momentum of a particle with arbitrary accuracy. You cannot simultaneously determine the position and the momentum of a particle with arbitrary accuracy. This was the statement of Heisenberg's principle. Now see why I'm telling you all this. Look at over here. Now let's say that you have a wave. Let's say you have a wave of a single wavelength. This wave is a single wavelength wave, and this continues up to infinity. So this is an infinitely long wave. So what is the wavelength of the wave? If I ask you the wavelength of the wave, you would say that the wavelength of the wave is lambda. So you precisely know with arbitrary accuracy the wavelength of the wave. And remember, if you know the wavelength of this wave, then you also know the momentum of this wave, that is given by the de Broglie hypothesis, that is h by lambda. So if you know lambda precisely, then you know the momentum precisely. So this wave, which is extending up to infinity, you know the momentum precisely. But if I ask you where is the particle that this wave is representing, then the uncertainty in the position is infinite. So you see, the uncertainty in momentum is 0 because you exactly know the wavelength. It is a single wave. So there is no uncertainty in determining the wavelength. In other words, there is no uncertainty in determining the momentum of this wave according to de Broglie hypothesis. So absolutely no uncertainty in determining the momentum because the wavelength is known. So, but what is the position of this of the particle that this wave is representing? You see, the uncertainty in the measurement of position is infinite. The particle can be anywhere extending up from minus infinity to plus infinity. So delta x goes to infinity. This is in accordance with the Heisenberg's uncertainty principle. Now, if you add many waves, then instead what you get is a wave packet. You see, this wave packet has a certain dimension, or in other words, it is localized in space, right? Please understand, if you add more and more waves, this wave packet is going to become more and more localized. So let's say if you add 100 waves, the wave packet is going to look like this. And if you add, let us say, 1000 waves, the wave packet is going to look like this. So you see that if you add 100 waves, the uncertainty in position is this. Because you remember, the wave packet represents a particle that is localized in space. So this wave packet represents a particle. Again, this wave packet represents a particle. But this wave packet contains many more wavelengths than this. It contains, let's say, 1000 wavelengths. So the underlying oscillation is kind of like this going on. And here you have the underlying oscillation like this. So you see, you are adding more and more waves. By adding more and more waves, you are localizing the wave packet. That is, the uncertainty in the measurement of position is decreasing. So you can, in this case, you can, with lower uncertainty, you can say where the particle is. Here you have a greater uncertainty. But look, when you can tell that particle is, okay, the particle is within this range, delta x. But in doing so, what you have done is, you have added more and more waves. Since you have added more and more waves, if I ask you what is the wavelength of this wave packet, the uncertainty is much greater than this case. Because in this case, you have added, say, 1000 waves of different wavelengths. So the uncertainty in wavelength is high. In other words, the uncertainty in momentum is high. But since you have added more and more waves, you have made the wave packet more localized. So the uncertainty in position is lower. So uncertainty in position is lower, but in doing that, in making the wave packet more and more localized, you have to add more and more waves of different wavelengths. And since you are adding more and more wavelengths of different wavelengths, you are not sure about the wavelength. And since you are not sure about the wavelength, you are also not sure about the momentum. So you see, you make this wave packet by making a localized wave packet. In order to make the wave packet more and more localized, you need to add more and more waves of different wavelengths. So waves of different wavelengths getting added up will give you a localized wave packet. So in a localized wave packet, the uncertainty in the measurement of particles' position is very low because the wave packet is localized. But again, remember, in making that packet localized, you are adding more and more number of waves of different wavelengths. So you are not sure about the wavelength. In other words, you are not sure about the momentum. So if you are sure about the position, you are unsure about the momentum. And if you are sure about the momentum, like in this case, you are sure about the wavelength, a single wave, you are unsure about the position. Right? So this concept of group and phase velocity is also helpful in understanding the exact concept of uncertainty principle. So now we'll be going on to the postulates of quantum mechanics. So